This is Lewis dot diagrams, which is also known as electron dot diagrams. And this is the first lesson for Chemistry 20. Note that you can find a full set of my notes available for you to print and just follow along to fill in the examples if that is something that you wish to do. So at the beginning of some of my lessons, I'll have some quick questions, and typically what I would do is have you pause and complete these, and then I'll quickly go through them and we'll continue on. These are usually questions that pertain to this lesson of information we may already know, or maybe it was from our last topic. So pause this and go ahead and answer the quick questions in the gray box at the top of your notes. So what is the difference between a core and a valence electron? What we'll do is we'll draw the full electron configuration for maybe magnesium here. So magnesium is in the third period or third row of our periodic table. Therefore, we are going to need 3 electron shells. The first shell is full of 2 electrons. You cannot draw them separate. The second shell is full and it has 8 electrons, representing a full second period that we have to cross before we get to magnesium. And then the last one, it has 2 electrons because magnesium is in the second group or column. So the difference between a core and a valence electron. Core electrons are all of the electrons for full valence shells. So core electrons would be represented by our first level and our full second level. So a full valence shell, or maybe I should say shell. Valence means typically we talk about the valence shell being our outer shell. So a valence electron is found in the outer shell. So in this case, a core electron or valence electron, and I abbreviate electron as E negative, is in the outer shell or the last shell. So in this case, we have 2 valence electrons. We have 8 plus 2 core electrons, so 10 core electrons. And magnesium has a total of 12 electrons, which is its atomic number. Draw the Lewis dot diagram for nitrogen. So nitrogen, when we are talking about a Lewis dot diagram for something, we're really only looking at valence electrons from here on out. So nitrogen is in the 15th group, and what we're going to do is we would count across counting elements in that row that we find nitrogen in. So if you've got your periodic table in front of you, we would count lithium, beryllium, boron, carbon, nitrogen. So 1, 2, 3, 4, 5. This means that nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. Remember, we work around the element, adding 1 electron on each of the north, south, east, and west, if you will. And then once we've gone around once, we can go around the second time to pair. What is the role of each of these electrons? So in nitrogen, bonding and lone pairs, that's what we need to talk about. This is a bonding electron. And in fact, so is this and this. So bonding electron is an unpaired electron. Therefore, a lone pair is the one that is actually paired up. So an element can have none or up to 4 lone pairs. An element could have 1 and up to 4 bonding electrons. What's the role of each of these? A lone pair doesn't really do anything super exciting. It just takes up space. For our purposes, we'll say that. Later on in chemistry, they do have some reaction ability, but we really just talk about them as taking up space right now. Bonding electrons can do just that. This is where we can bond. Because nitrogen has 3 bonding electrons, nitrogen typically wants to make 3 bonds. So if we were to look at something like oxygen, for instance, oxygen's Lewis dot diagram looks something like this. It has 2 lone pairs and it has 2 bonding electrons, meaning oxygen would like to make 2 bonds if possible. So in bonding, atoms can share or transfer electrons to become stable. And this only works if they stay close enough together, resulting in an attractive force. So atoms that are super far apart have a harder time bonding than atoms that are super close together. They're more likely to bond where they're either sharing some of their electrons or there's a full transfer happening. So we can call the next 3 types of bonds intramolecular forces. Intra means bonds within the compound itself. So the first example of an intramolecular force is an ionic bond. So an ionic bond is created by the simultaneous attraction between a positive and a negative ion. And those positive and negative ions are created by the transfer of one or more valence electrons. So there's no sharing in an ionic bond. An ionic bond can also be known as an electrostatic attraction. Electrostatic meaning the attraction between a positive and a negative. The metal always donates electrons to nonmetals until all atoms, or now ions, because we've started moving electrons around, have a full octet, okay? Or look like a noble gas in terms of their valence shell being full. We'll take a look at this. Covalent bonds are when 2 or more atoms share bonding electrons to make a full octet. How do we draw Lewis dot diagrams? Well, there's a bit of a process, and the reason is, and I'm going to skip ahead to our very first example, SO2. If you try and draw SO2 by our generic form of kind of writing out what we know about each element. So sulfur has 6 valence electrons, oxygen has 6 valence electrons, and I'm going to draw this one over here, sorry. 6 valence electrons. So if we wanted to start pairing these, I would pair these 2, and I would pair these 2, and I'm left with 2 unpaired electrons. Now that's not really something that happens. So our natural tendency would be to say these 2 electrons must pair. So once I have a pair of electrons that are going to be shared, they create one bond. So I can have a sulfur here and it's bonded to an oxygen. And now remember we have to add in our lone pairs. And that sulfur was bonded to another oxygen which had 2 lone pairs, and these 2 oxygens were bonded together. So again, a bond represents these 2 electrons sharing between themselves. Now what this looks like is a big triangle where we have sulfur, oxygen, and oxygen. And this is actually not what SO2 looks like in real life. So our matching of electrons works in a lot of cases. However, there are some exceptions where it's not going to work, and we're going to have to go through this process. So bear with me. I'm just going to go through the list of what we have to do, and then we're just going to put it into play with some examples. Okay. The first one being the correct drawing of SO2. So we're going to calculate the total number of valence electrons in our compound. And that again is by counting across our periodic table. We do not count core electrons. If the entity is a polyatomic ion, so one of those listed at the top of our periodic table, we're going to add or subtract electrons to the total count to account for the net charge. I have an example for this, so don't fret if you're like, what are you talking about? Select a reasonable skeleton for the molecule or polyatomic ion. So the element with the most bonding electrons, so the most unpaired, electrons is our central atom. And we'll work outwards from there. You can have multiple central atoms. Oxygen atoms don't really want to bond with one another, except in an O2 compound and an O3, when this is all by itself. Okay, when there's basically no other option. For ions or molecules with more than one central atom, the most symmetrical skeleton possible is used. We're going to connect all atoms in the skeleton, and every time we connect, we're drawing a bond. One bond is composed of 2 electrons being shared between those 2 elements. So what we'll do is we'll subtract 2 electrons from the total number of valence electrons to account for each bond drawn. We're going to place the valence electrons on the outer atoms first, and then we're going to work our way onto the central atom as lone pairs. If it's not complete, the octet, we're going to move a lone pair from an outer atom or a peripheral atom to a new position between the peripheral or outer atom and central atom. Repeat until everybody has a full octet. For ions, we end up with square brackets around the entire Lewis formula or Lewis dot diagram, and we will write the net charge outside of the bracket. Now that seems like a mouthful and a list of rules that don't make sense, so let's get started with some examples. So we're going to draw the following Lewis dot diagrams for the following compounds and polyatomic ions. I'm just going to give myself some space here. Let's start with SO2. So SO2, we're going to count the total number of valence electrons. So valence electrons, sulfur had 6 valence electrons because it's in group 16. We count all the way across period or row 3. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur. That's 6 elements in. So sulfur has 6 valence electrons to contribute to our total. Oxygen also has 2 valence electrons. And because we have 2 oxygens, we're going to multiply the number of valence electrons by 2. So 6 plus 2 times 6 is 18 valence electrons total from S and 2 O's. So we are going to work on the next step here, which is select a reasonable skeleton for the molecular polyatomic ion. So the element with the most bonding electrons is the central atom. Well, if we took a quick look at what these looked like, if you don't remember from our previous page, they each have the same number of bonding electrons. So now what? We're going to try and select the most symmetrical. If we're going for symmetry, sulfur goes in the middle and oxygen on either side. Once we've drawn a little skeleton of where we want to put our elements, we're going to connect them. So I'm going to connect my oxygen to my sulfur and my sulfur to my oxygen. I've drawn 2 bonds. Now each bond is 2 electrons being shared. Therefore, I have used or put into my diagram 2 4 electrons. So I'm going to subtract 4 electrons from my total. This leaves me with 14 electrons that I still need to put back into my diagram. I'm just going to switch to a different color so you can see maybe some of my steps here. We work on our peripheral or outer atoms to complete the octets by placing the electrons in pairs. So oxygen currently only has 2 electrons around it by this bond. Remember, it's shared. So I need to fill its octet up to 8 by adding pairs of electrons. So 1, 2, 3, 4, 5, 6 electrons fills that octet. I'm going to go over to my other peripheral or other outer atom. Remember, sulfur is my central atom. And I'm going to fill its octet. So with another 1, 2, 3, 4, 5, 6 electrons. So I've used 6 electrons on each. That means I've used a total of 12 electrons, and I need to take that away from what I still have left in the bank, if you will. Oops, that's not 0. That's 2 electrons left. So what do I do with those 2? I'm going to place remaining electrons on the central atom as a lone pair. So I have 2 electrons, that's 1 lone pair. I'm all out. Once we're at 0, I can't add any more dots or bonds. I can only move things around. So my little caveat there says, if it is not complete, we're going to move electrons around. So let's count things up. Around my oxygen, I have 2, 4, 6, 8 electrons. So oxygen has a full octet. We consider it happy. It's good to go. Little check mark for it. Oxygen over here has 2, 4, 6, and remember there's 2 electrons here, 8 electrons surrounding it, so it does have its full octet. It's good to go. Looking at sulfur, sulfur has 2 electrons in this bond and 2 electrons being shared in this bond, so 2, 4, 6 electrons. Sulfur doesn't currently have an octet. So what we're going to do is we are going to move electrons from an outer atom's lone pair to share between the two. Now, because it doesn't matter who I share from, it's the same. I'm sharing from an oxygen to the sulfur. I'm just going to borrow this pair of electrons and I'm going to put it into this bond. So I will redraw this for us as oxygen. This oxygen still has 3 sets of lone pairs bonded to a sulfur. This now has 2 bonds, one from its original, and the second one is from that lone pair moving inwards, bonded to an oxygen. Oxygen now only has 2 lone pairs left. Now we can double check to see if everybody's happy. Nothing's changed about this oxygen, it's still happy. Over here, this oxygen has 2, 4, 6, 8 electrons, it's happy. And sulfur now has 2, 4, 6, 8 electrons, it is happy. This is our final answer. Okay, we're going to try methanoic acid next. So these are all a little bit of examples that I wanted to go through because there's something happening in each of them. So let's count our total number of valence electrons over here for methanoic acid. So HCOOH. So hydrogen has 1 valence electron. A carbon has 4. Each oxygen has 6. And I have 1 more hydrogen at the end. So I'm just trying to add them in order for you guys to be able to follow along. So 1 plus 4 is 5, 6, and 12. We have 18 valence electrons again, but in a different diagram. We need to decide who our central atom should be. The element with the most bonding electrons is our central atom. And if we looked here, we've seen oxygen over here. Hydrogen has 1 bonding electron. It should never really be a central atom because it doesn't like to bond too much. And carbon has 4. So carbon is a great central atom, and we're going to put carbon in first. I'm going to put a hydrogen on this side. And then I have 2 oxygens to fit in. So I'm going to put an oxygen on each side of carbon. Because remember, oxygens don't want to bond together. Okay? And last but not least, this is trying to tell us the order of things. The O and this last H go together. So I'm going to put my last H here. So sometimes a formula is written out a little bit further. We could have condensed this to CH2O2, but that doesn't tell me much about the connectivity. So organic compounds like this guy here, we expand its formula to try and show a little bit more information. All right, this is our skeleton. And what we're going to do is we're going to connect all atoms within our skeleton here with a bond. We're going to subtract electrons from our total based on how many bonds we drew. We drew 1, 2, 3, 4 bonds. Each bond is 2 electrons. Therefore, I just used 8 electrons in this diagram. I'm left with 10 electrons to put back in. So we're going to place pairs of valence electrons on outer atoms to complete their octets. My first question is hydrogen happy? Hydrogen actually only wants to bond once. So we don't need to fill up hydrogen's octet. It would be incorrect to draw electrons around hydrogen like this. So we don't do that. What we're going to do is we are going to fill up other atoms instead. So I'll switch colors so we can pay attention. We have 10 electrons to put in, and hydrogen doesn't need any. So we're going to work on the other outer atom. Next outer atom would be oxygen. So 1, 2, 3, 4, 5, 6 electrons. And I still have, about 4 left. Now, what we're going to do is we're going to work inwards. Technically, carbon was our first central atom. So I'm going to work by putting oxygen, giving oxygen the next round. So I put 2 more lone pairs to fill up its octet, and I need to subtract 4 more, and I'm out of electrons. Let's check if everybody's happy. Hydrogen here is happy. Oxygen here has 2, 4, 6, 8 electrons. It's happy. Hydrogen's happy over here. Oxygen currently has its full octet, 2, 4, 6, 8 electrons. The only one who's unhappy is carbon. So here's where we need to decide, who are we going to borrow from? In the case of SO2, it actually didn't really matter because it was the same on both sides. But over here, I have 2 options of where to borrow from. I can borrow from this oxygen or this oxygen. And although they're both oxygens, they're not the same in this compound. So let's back up and we'll look at our original diagram here for oxygen. Oxygen wants to make how many bonds? Well, 2, because it has 2 bonding electrons. So let's see how many bonds each oxygen has made here. This oxygen has made 2 bonds, 1, 2. So it's actually okay with what it's done here. It would rather stay as it is if it could. It's happy to add some electrons to the pot here and share some extras, but if it doesn't have to, it won't. Checking this oxygen's only made 1 bond. So it's happier to volunteer its electrons to the cause here. So let's move a pair of electrons. It doesn't matter which ones you select. And we're going to make a double bond. We'll see how this looks different. A double bond, and we have 2 pairs here. We can double check now. Everybody's octet is good. Nothing's changed about our hydrogens or oxygen here. Carbon now has 4 bonds, so 2, 4, 6, 8 electrons around it. This oxygen has 2, 4, 6, 8 electrons around it, so everybody's octet is happy. We can also check to see about this bonding. Again, each oxygen would like to bond twice if it could. This oxygen has bonded twice, and this oxygen has bonded twice. So this is the best representation of methanoic acid. All right, last 2, ammonium. Ammonium is a polyatomic ion. Just draw myself a little grid here so we don't get confused. Ammonium is NH4 plus. So let's add up our total number of electrons. Nitrogen has 5, and each hydrogen has 1. Now a positive means that if we've started at neutral, to get to a positive, we have lost an electron. Therefore, we subtract 1 from our total. So 5 plus 4 is 9, minus 1 is 8 electrons. Now notice that everything exists in pairs. So if you ever get an odd number, you know that you've done something incorrect. Okay, hydrogen makes a terrible central atom because it only ever wants to bond once, which doesn't make it very central. So nitrogen's going to go in the middle, and I'm going to put a hydrogen on each side. Remember, I can only ever fill the northeast, south, and west side of an atom for it to fill its octet. Okay, connecting everybody. I've added 4 bonds. 4 bonds, each bond having 2 electrons, means that I've used 8 electrons in my diagram. I'm all out. So I have to skip to the point where we check if everybody's got a full octet. Does nitrogen have a full octet? Well, 2, 4, 6, 8, it looks good. Hydrogen, does it have a full, and I use octet, I guess, loosely, because it only ever wants to have 2 electrons. Each hydrogen is bonded once. It has 2 electrons around it, so they're happy. We're done. The only thing is, it says for ions, place square brackets around the entire Lewis formula and write the charge outside the bracket. So because we've added or subtracted electrons from our general count, to get this, we have to draw square brackets and we'll put its charge out. Last one, NO3. NO3 minus. Nitrogen had 5 electrons. Each oxygen has 6 electrons. And a negative, to go from neutral to negative, we've gained an electron. So we are going to add an electron to our total. 3 times 6 is 18, plus 1 is 19, plus 5 is 24 electrons total. Nitrogen has 3 bonding electrons, whereas oxygen only has 2. So I'm going to put nitrogen in the middle, and I'm going to put my oxygens around. Connecting, I'm going to connect, and I've used 3 bonds, which is 6 electrons. I'm left with 18 electrons to place back in my diagram. Filling in my outer atoms first, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons. So subtracting 18 from my total, I cannot add any more electrons. The only thing I can do is borrow. Now, looking at all of the options, I can borrow a lone pair from any of my oxygens here. All oxygens look the same, so it doesn't actually matter who I borrow from. On your pieces of paper, you don't have to redraw if you don't want. What I'm going to do is I'm going to say I'm going to borrow from this guy right here. And I just erased them really well on my page. Thankfully, my iPad just lets me do it as is. And those 2 electrons are moved in between to act as a bond. Now, everybody's octet is filled. Nitrogen has 4 bonds around it, which is 8 electrons. And every oxygen also has 8 electrons. The last step here is we need to draw square brackets because this was an ion. It had a charge of -1. All right, that was a long part of our lesson, and there's lots of practice. So please make sure that you do some practice on this one. The last type of intramolecular force is metallic bonding. So we've talked about ionic bonding, which is a metal and a nonmetal. And we've talked about covalent bonds, which is 2 nonmetals, or we can even draw those polyatomic ions. And the last one is metallics. So all atoms share all of their valence electrons. Valence electrons are said to be delocalized, or they make a sea of electrons. Positively charged metal ion in a sea of negatively charged electrons is a metallic bond. Now, what on earth is that? Okay, here's the example. So a metal, here's the metal atom itself, is made out of a positive nucleus, and it has lots of core electrons that it's still held on to here. However, it's let go of its valence electrons. Its valence electrons are floating around here. I couldn't tell you whose electron is whose here. They just let them go when they're all together. All right. Now, when they're all together like this, they have free electrons, and electrons are able to move throughout all of these because the negative is attracted to the positive. It could be attracted to this one, it could be attracted to this one, it could be attracted to this one and move a little bit over here, or it could be attracted to this one and moves a little bit further over here. You get the idea. These electrons can move. So they are delocalized. They do not have to stay in one place, and they create a sea. They're just kind of swishing throughout here. Okay, our atoms that are now positive ions stay here. They don't move. Just our electrons are free to move because they are so small they can move in between the spaces. So for example, let's use magnesium as an example. So magnesium had 2 valence electrons. So when I draw magnesium, it's going to give up its 2 valence electrons. So I'm going to draw a few of them, Mg2+, Mg2+. And now each magnesium had 2 electrons to give up. So I need to draw 6 electrons somewhere in here to give the idea that it is still balanced overall. As a piece of metal, we had 6 electrons, and we have 3 magnesiums that are a 2+. Therefore, overall, we had a 6 positive charge. Together, 6 negatives and 6 positives make a neutral. So metals are neutral overall, but these electrons are free to move throughout. The number of electrons depends on the valence electron count for each atom. So top 3 ideas, I give you space for these in all of my notes. What are the top three the top 3 or maybe less major ideas that were presented in class today. List them in point form to highlight important ideas to come back to when studying for quizzes, a unit test, or a final exam. It just helps to kind of consolidate your understanding. Additionally, I will always post homework. These are for your practice. I will never ask you to submit them. This one I think is really important just to get us started is the Lewis Structures worksheet. It's a handout that I would normally print, but I've posted it online. What you're going to do is you're going to draw the Lewis dot diagram or Lewis structure of your compound. So the first one is H2O2 and then there's CO3 2-. So you're going to fill in the box where you can draw it. And in the box on the right hand side, if you're looking at this assignment, you're going to fill in the total number of electrons. Everything else, like the general formula, Vesper shape, angles, polar, nonpolar, and 3D drawing are something that are going to come next. So don't lose this sheet. You're going to keep it so you don't have to redraw Lewis dot diagrams every time we come to things.